Hi, everyone. Thanks for joining us today. We'll get going here in one moment, but I'll go over a few things while people are joining us. First, the webinar is being recorded and we are going to be sharing that link. I will include a link to a shared folder that includes a certificate of attendance and some additional resources that you can find there. And feel free to ask questions. We've got two former physics teachers, Tom and Dave, and then Sam is going to be helping answer your questions along the way. So we'll be monitoring chat, and feel free to put questions in the comments there. And with that, I will pass it over to Tom and Dave and Sam.
Hi, I'm Dave. Can you see me there okay? All right. I'm Dave Vernier. I founded Vernier Software and Technology, but I was a physics teacher, and I've been promoting the concept of introducing a little bit of programming to a physics class for a long time. Starting back, and this book was written in 1986, and it really was about having kids use Apple II computers and some electronics and write little programs to do things. And I've been continuing to promote that kind of concept for all these years. We've done it with, first it was BASIC, and then we did it with LabVIEW, we've done it with Arduino, we've done it with all kind of block-based languages like Scratch. And now we're trying, and we're going to talk about here, Python and VPython. So why in the world would a physics teacher want to introduce computers into their class? It's a physics class after all. And I think there's a whole bunch of good reasons. One is, it may be that some kids aren't going to be introduced to computer programming anywhere else. And everyone should at least have some handle on writing a program and knowing what a program is. What I hate to see is a person who thinks this thing is like magic or something. It isn't magic, it's just a whole lot of programming. So I think that's real important. Another thing is, if you can learn just a little bit of programming, you can sure do wonderful things for projects. Science projects are just projects that come up as part of running your physics class, or a kid doing a special experiment, taking it further. The third reason is that you can learn a heck of a lot of science by writing a science program. It's just the nature of the beast. You can't write a program studying the motion of a cart without learning a heck of a lot about how physics of dynamics and motions of carts work. It's just the nature of the beast. And finally, I think it's using computers in your class can really spice things up and be great fun. And I think we'll show you some of those things today. And we'll be happy to answer questions. I can't resist showing some more books. We've been doing this for a long time. We did a book about using Lego stuff years ago. This is one using LabVIEW for projects. So we've been doing lots of this projects and learning a little bit of coding stuff. So I think I'll now turn it over to Tom. He's going to show you some of the basics, and then I'll come back on and show you some of the fun things I've been working on. I really do think that this Python and VPython have made everything that I've talked about, it's so much easier now. And, you know, in the old days, it used to be a huge struggle sometimes to buy the software, to do coding, to install it. Now things are so much easier and often usually free, frankly. So I'll turn it over to Tom.
Thanks, Dave. So I'm going to share my screen here in a minute and show you some of the resources that we have available for you to engage with Python and Vernier sensors, and show you a couple of examples. I can't resist throwing in my 2 bits of why I think coding, especially in a physics classroom, is important. It does provide for another avenue for students to engage with physics content who may not be drawn to physics, but are drawn to coding. So just another avenue to be exposed to the content, and it provides another avenue for a different learning style as well. And then in addition to that, there are also tools when you get into coding that provides solutions to physics problems that can't be solved analytically. So it's just kind of a nice thing. I see that Angie just put in the chat the link to the resources for the webinar. And with that, I'm going to start sharing my screen and show you some of the other resources available. Okay, so you should be seeing my screen now. I just typed in Python into the search engine to come up with this page. Talks a little bit about why you want to code in Python with Vernier sensors. And you scroll down a little bit further and you see this screen of Python and GoDirect sensors, Python, GoDirect and Raspberry Pi, and Python and LabQuest sensors. So we have libraries for using our sensors with Python, both for our wired sensors, what we call our LabQuest sensors, and for the GoDirect sensors, the sensors that you connect via USB directly or by Bluetooth. These two resources for Raspberry Pi and for Python GoDirect sensors are essentially, they take you to the same place because a Raspberry Pi is just a small computer. So just be aware of that. So I want to explain a little bit about what you would see if you go to this guide. So this takes you to a place where you can get started with downloading Python onto your computer and installing a library that allows you to communicate to your Vernier sensors with Python. So there's a good getting started guide here. A lot of tips for making this all happen. And then further down, there's some troubleshooting guide for what happens when things don't work, as well as examples, links to examples. This is all just available on this download webpage. The actual programs, if you want to download our starter programs, our example programs, you do that on GitHub. And we can get there by clicking here, view on GitHub, and just go to Python. This is all for GoDirect examples. So this has JavaScript, Python, and VPython examples. I'll just click here to just show you, you would have the opportunity to access these files here, as well as this getting started guide. I'm going to back up a little bit. This first page that we landed on and go on GitHub, this is where you can download the code. So this would allow you to download a zip file with all of our example files. So that's a good place to get started. Let's see, let me go ahead and I'm going to show you a couple of examples. So I'm going to reduce this for now. Python, installed Python that you've installed on a computer comes with a development environment called IDLE. And it stands for an integrated development environment, learning environment for Python. You can use other editors, but this one comes with and is a good starting place. So this is one of our starter programs. It happens to be the analog LabQuest sensor. So you just see that in this case, in Python, we have this line of code that imports our library once you've already installed it on your computer. And then these LQ lines of code that start with LQ are all tied into the library. So here we open the sensor, we select which channel we're connected to with our sensor, and we set a data collection rate here, 1,000 milliseconds or 1 second. And then we have a loop here. And at the end of the loop, once you've run through this loop 10 times, you're going to stop data collection and you're going to close the LabQuest. These are kind of the generic parts of code that you would need to include in Python in order to communicate with our sensors and shut them down, start them up and shut them down appropriately. Just to illustrate this, I have a LabQuest Mini and a gas pressure sensor connected to my computer by a USB cable. And I'll go ahead and run this program, and I'll change the pressure with the syringe a little bit so we can just collect some data. It's a pretty basic program, not a lot of code here, easy access, low barrier of entry for getting started with this. So I hit run module, and this opens up a window that allows me to read out the values of the pressure, depending on whether I'm pushing or pulling. And after 10 data points, it's going to stop data collection, get ready for the next set of data. Again, pretty simple program, just to illustrate that you can collect data very easily with our LabQuest sensors. I'm going to do the same thing with a little bit different program for our GoDirect sensors. I'll show that in just a minute. So let me go ahead and pull that up. So there's the next program I want to run. Now this program has 2 libraries we've imported. The first one I'll mention is our library, the GoDirect library. We abbreviate GoDirect GDX, just shorthand for us for GoDirect. And so we import the library into this program just by calling import GDX. We've also included VPython, which is a visual tool within Python, another library that you can call that is going to open up a web page and show some visualization of the data that we've set up here. You'll notice instead of having LQ code, in this code we have GDX code. Those are the lines of code related to the GoDirect library. We can connect either by USB or Bluetooth. We can just change that USB to BLE if we want to go ahead and connect by Bluetooth instead. This allows us to choose the sensors, and then this sets up that screen in Python. Let me bring up my web page so that we can see that when we get rolling here. So I'm going to go ahead and again hit run and run module. You can also use F5 to do this. And I have the wrong program running, so I'll just let the LabQuest program run again. And so I don't do that again. I'm just going to close these windows completely and bring up the other program. Here we go. Okay, so now we're connecting by USB. This is the GoDirect sensor. And before I get going with that, I'll just mention that I'm using the light and color sensor here. And we'll see in a minute that there are a number of sensors built into this. There's a light sensor, a UV sensor, and a red, green, and blue sensor. So we'll take a look at that here momentarily. Get this back up here where I want to be and bring this up. Okay, so we're going to run the module. And in the shell, the editor always pops open this shell to illustrate the information. We see that there is this light sensor, the UV sensor, and then our red, green, and blue sensor channels. So we can choose which channel we want to use. I'm just going to use the light channel. So I'm going to enter 1 and hit enter. And you'll see that this popped open a web page. And I have this picture. So I'll go back to the, well, maybe I can do that right now. We'll pull up the program right alongside here. So this canvas, this is what we call the canvas, has a sphere, that's the red sphere right there, and a rod. So this transparent cylinder that we see here. And we have basically tied the data collection, so these measurements that we're taking from our GoDirect sensor, and we're using that to adjust the position, the Y position of the sphere by taking that sensor data and moving the ball with that. So I'll go ahead and hit collect here, and you'll see that right away the ball is way up above. So I'm adjusting the height of my sensor so that it doesn't get quite so much reflection there. And I can zoom in. So this is actually a 3-dimensional picture here. I can move this around side to side, up and down. And then if I go ahead and take a chance and turn off that light so I can show that if I block that light altogether, maybe it'll help to see what I'm doing here. If I move this side a little bit. So if I block the image of the light coming in contact with the sensor, it goes down. And then if I turn on the LED, you can see it go up a little bit. I can bring a light closer, reflecting closer. It's going to be a brighter light. Just kind of a cool way to see that interaction between the visual Python and the sensor data. So I'll just go ahead and stop that and close that that program, and it just blinks the web page, and I'll close that now as well. So that's an example of our LabQuest sensors with Python and our GoDirect sensors with Python. Again, these are, this is the Python that you have installed on your computer. The next thing I'm going to show you illustrates how we can some value from using a web VPython, which is a resource that Bruce Sherwood created really to help us introduce physics concepts in a really easy fashion and demonstrate, illustrate them very simply and straightforward. And we have been able to integrate web VPython with our sensors thanks to his help. So a lot of this is on the back of Bruce Sherwood's efforts to integrate our sensors with his program here. So if you create a web VPython account, you're just ready to start programming on the web. So if your students have Chromebooks, this is a great example. You do need internet access to use the web VPython version here. Well, I'll show you my list of programs here. So if I go to my programs, look at the list of programs, we're going to take a look at one in particular, this color match solution, where this is an example of something that you can't do in just regular data collection software. So we're going to take advantage of the fact that we have a red, green, and blue sensor wrapped up in this Go Direct light and color sensor. And we're going to look at the different components of the light that are being reflected to the sensor. And then we're going to recombine that. So I'll show you that program here. This is, again, just all web-based. So here's VPython. This is the library that we've created to work with VPython. And it allows you to connect our sensors and has commands that are, if not identical, very similar to what we use for our commands in Python that you've downloaded onto your computer. So here we have, I've created a series of boxes, and I'm using a USB connection. These sensors, 5, 6, and 7, those are the channels for my red, green, and blue sensors. And I'll just illustrate this and we'll come back and look at the code again. So in order to run this, because it is a web program, there are some security issues that make it a little bit more challenging, just a few more steps to actually get it to run. I have to click this share or export program, and then I have to download it as an HTML file. So one nice thing is kind of a check to make sure you've coded it correctly. If there's code that shows up here, it has compiled correctly. So this is basically JavaScript with a translator to take your Python code and convert it into Python or to JavaScript so it can be presented on a web page. So I'll go ahead and hit the download HTML. And now my program shows up down here as an HTML file. I click on that to launch it. And we see this screen pop up. So here's my canvas. Here's a graph of data. And I should be able to just collect or connect to my Go Direct sensor here. So I'll hit connect. And connect there. And then you can see right away, if I just move my hand under here, the live readout occurs right in here. Nothing's happening here yet until I hit collect. So I'll go ahead and hit collect. And then we can see if I bring my colored card up here, we get the components red and green, and then we get a color match. So I've basically recombined those signals for the red, green, and blue components to recreate that color. I can do the same thing here. I'll get a tealish color that has some green and blue, a little bit of red in there. And let's do just what looks like a pretty solid green, has a little bit of red and a tinier bit of blue represented there. So kind of a nice way to engage with if you're doing an activity with your students where they are studying color and color mixing. They can see how this actually works by creating this program, maybe get some coding experience at the same time. So I think I'm going to stop now, and I'll stop sharing my screen and turn this back over to Dave. So if I can figure out where I need to go to stop sharing. There we go. Okay.
All right. I think I'm back on. Okay, I'm going to share my screen, but I'll just make a couple comments before I do. First of all, Tom does a great job explaining that stuff, and that's great. I would just emphasize that especially the web VPython is just truly amazing. We love Python, but sometimes it can be a real pain to get Python installed on a computer. So we struggled like crazy with that, and I know teachers don't like doing that either. And then we discovered this web VPython, and then miraculously we were able to get our sensors to work with the web VPython. And so that you can do with zero installation and be doing this really cool stuff like that color thing is, to me, just amazing. Also, I really want to stress that this is a Chromebook solution. And as we all know, Chromebooks are a big deal in education right now. We can't do the installed stuff on Chromebooks. So those are two huge advantages. I'm going to try to share my screen, and I'm going to do just web VPython stuff. And I'll show two kind of more razzle dazzle things. Tom's shown how easy it is to get started, and I guess I'm showing possibilities here. So let me try to do this. Are you seeing my code there, Tom? Okay, this is a program that I wrote for showing simple harmonic motion. This would be a classic physics thing that you might want to do with your students. I'll run it first, and then we'll go back and look at the code. Now, because of the security stuff, as Tom showed, you can't just do run, it won't work. Instead, you do this share and export, then you do this download, and then you get a downloadable file which you can click on. Now, this is a simple harmonic motion demonstration. And I guess I better get some motion going. I've got a GDX motion detector there, and a spring and a mass. That's 500 grams. And I actually measured the spring constant, and I put in the mass, and I can now choose a Go Direct sensor and connect. And you start to see the numbers changing here, but nothing's happened on the graph. But what happens if I hit collect? I'm getting data, and now, as Tom showed, this stuff is, to me, kind of amazing. This is all just a little bit of code, but it's almost like a real object. I can look at it from different angles. To me, this is like science fiction almost. And I can, these are arrows that I made showing the velocity and the acceleration. So we're trying to do whiz bang, showing what you can do. I even have a thing here now where I can choose modeling. So in the code, well, let's stop and let's look. No, I'll go ahead and do it. I put in code, we'll look at it later, where I model the motion of a simple harmonic oscillator. And I put in the correct mass and the correct spring constant, and you'll see it's pretty darn good. It's not perfect, but wouldn't this be a great exercise to experiment, have your kids challenged to do that? Let me show you the code, and it's not, that part of the code is not complicated. This is the standard web VPython stuff, and here's some title stuff, but here's the modeling stuff. I stretched that spring, and it took 1.5 newtons to pull it 10 centimeters, and I did the math, and I got that 15. And then I estimated I measured the equilibrium position and put that in 38 centimeters, and then I estimated I'd pull up about 7 for height, and there's the mass of the object. And then that turns into code down here, where I say if modeling checkbox is checked, you do the standard computational physics kind of modeling stuff. So to me, that's really a great example. Now you might say, well, that you got lots of code there, and it's kind of overwhelming, but you don't have to have all that stuff with the cutesy stuff. You could have a much simpler version. So, and we think there's lots more examples we could do like this. For example, next thing I want to do is a coffee filter falling lab. It's a lab we've been doing for years, where you drop coffee filters, and of course they fall with some serious air resistance. And wouldn't it be fun to model the position versus time graphs of those with computational physics and VPython, web VPython? Okay, I'm going to show one other demo. This one does not include a sensor, but I figured I should show it to you because it's something that's physics, and we've done it with web VPython. So let me go back here. It's called mapping electric potential. We have a lab in it's in our advanced physics book, where we have people take the black paper. Some of you have seen this conducting paper, and you put a positive and negative wire or object on the paper, and then you go around with a meter and you measure the volt potential at each of the points, and you get, the idea is to get a map of the electric potential. In the old days, we used to tell people to import that data into Excel, and then Excel does have a 3D plotting thing. So that was fine. But since we now have this web VPython, we thought it'd be pretty cool to do it this way. And so now this is a program with no sensors involved, so I can hit run. I don't have to do that share and export and then download. This runs a little slow because it's a big program, but I'll show you this, and it's kind of fun. And it shows the potential for the graphics. That's real data for velocity. So imagine, well, let's look at it from the top. If you were looking at it from the top, you were, well, here, I can do a 2D version later. But basically, that's a piece of paper, and we now I'm getting all out of control here, but get it back. We went around and measured the potential at every one of these black dots, and the rest of it's extrapolated. But there was a positive voltage here and a negative voltage here, and so you can see you get the shape thing. And of course, I'm showing off the incredible graphics. And this is a fairly fancy program, but it's not out of control, and we certainly will give this to you if you want to use it. So it would be an option. The way it would work is you would type in, you would use our graphical analysis program to take the readings at all those points. It's 143 points, and you you run the program. Excuse me. Then you export that data as a CSV thing, and this program here can import that and then do the graph for you, and or do a 2D plot or a 3D plot. So you'll see this is a fairly involved program, but it's yours to use if you want. I think I have time enough to do one more thing, promoting web VPython, which I do think is an amazing thing. If I go here, this is where I signed in, and if I go to here, if you click right there, you can come to, and here you can go to the examples provided by the people who did web VPython. Some of these, and these are all free, and you can use them and you can run them, are just amazing and good science. Like, for example, this is sort of showing the concept of what a molecule, what a solid is like with vibrations. Let me do the one though that this one here about this kind of simulating hard sphere gas model. So I can just run that, and it's showing you can do things. You can change the code so it has different temperatures, and I mean, I think that's kind of amazing stuff. So I guess I will stop at this point and see if there are questions or if Tom wants to jump in and say anything.
I'll just bring up that we have a lot of example code for all three of these types of connecting our sensors to with Python. So you don't have to start from scratch. We have starter code, and really it just hopefully opens up a lot of opportunity for your students to engage in coding and strengthen their understanding of physics concepts you're working with at the same time.
You know, another interesting thing about this webinar is a webinar promoting things that are, everything we're promoting pretty much is free. All the Pythons are free, as far as I know, and web VPython is definitely free. The amazing thing about web VPython is you can sign up for an account. All you need is a Google account, and you don't even have to give them your name. So there's absolutely no security issues with your students. It's not like they have to get the student's name or anything, or even their, I guess they get their email address, they get an email address, which this is tied to, but they're not asking for any information, and they don't charge anything for the account. And you do get a pretty good system for collecting your programs and storing them on their server. And it's all there just for you. So, we have to assume that they're backed up and stuff like that.
So Dave, there are a couple of questions in chat. One is regarding sharing this recording, and everybody who signed up for this webinar will get an email when that recording is available. The other question, the next question is a question from Eric asking about how to connect to sensors. So
Two sensors?
how to connect sensors in general.
Which kind?
So yeah, so maybe we should start with the LabQuest sensors.
You want me to go through that, or you want to go through that?
Yeah, if you want to handle that, that'd be great.
Okay, that would mean so just the concept of connecting to a sensor. You know, everything we've done so far, we've done by USB, so maybe I'll do one by Bluetooth. Let me share my screen. And are you seeing those vibrating dots? Because I still got that program running. Is that right?
Yeah, there you go.
Okay, now I'm going to go back to my programs, and I'm going to choose the world's simplest program. Oh, here's a nice feature of this thing. This is my part of the web VPython world, and I didn't pay anything for this, but it's here, and I can sort things by name and stuff. I want to run the simple. I want to run this one, just getting started USB. That's a world's simplest program by USB, but just for demonstration purposes, let's change 3 letters to BLE for Bluetooth low energy, Bluetooth low energy, I guess it is, right? Yeah. Now, if it's a program to connect to a sensor and read channel 1 of that sensor. Now there's going to be, you'll see something slightly funny here, because I happen to be next to where in our building we store dozens of sensors. So this will be a little out of control, but what the heck? We'll try it. So I run this now, and it's a very simple program. All it's going to do is change the size of that ball based on the sensor reading. But notice what's happening here. Since I'm at Vernier Software and Technology, there's a whole lot of sensors. So I've got to find which one to connect to. And it turns out this little wedge thing is a nice indication of how strong the signal is. And so it helps me find it. And I see it there as G6. Yep, G6. So I can hit that one and say pair. And now I notice I'm getting a reading. This is a force sensor. If I pull and push on it, the sensor reading changes. And now here, just for fun, let's hit collect. And notice also I can change the data collection rate here. And I can even change channels, I believe. So if I wanted to say, let's change to acceleration, I tell you the truth, I haven't tried this for a while. I think, yeah, this works fine, I think. So if I tilt it, so it's reading the accelerometer. And another interesting thing about connecting is I can add another sensor. So you can actually connect multiple sensors. I've never tried more than 2, but we do 2 fairly often. I'll stop sharing. Other questions we should talk about?
Yeah, I guess the only thing I'd add to that, Dave, is if you're using a LabQuest sensor, you do need to use a LabQuest interface. You can't use a Go link, for example. So you'd have to have a LabQuest Mini, or I assume original LabQuest would work as well as LabQuest.
Yeah, they do. I've tried that. What won't work is for the old timers, Lab Pros won't work either.
Yeah. So I saw that there were some questions earlier on about using web VPython with iPad, and you could certainly do that. You couldn't do sensor data collection though with that, at least not with our sensors. Is that true?
Yeah, I tried that. I asked one of our programmers, and he said it might be possible in the future, but certainly not now.
Not at this point. But Chromebooks, computers work great. So that's wonderful. There's a quick question in there about the GoDirect cart. That should work. I haven't tried it myself, but any GoDirect sensor is going to send out a signal that you can integrate into your web VPython or Python activities. You bet.
Yeah. There's a few obscure sensors that don't work well. Things like, they tend to be really high-end, expensive things like spectrophotometers, gas chromatographs, polarimeters, and then another thing, and this is a physics seminar, so this shouldn't be too important, but things like blood pressure and heart rate, you could do it, but the program's just going to send out a signal. Maybe in some cases it'll do the math, but you know, we're talking about here mostly simple analog things: pressure, temperature, light, you know, UV level, carts, motion detectors, stuff like that. And the interesting thing is, you don't even have to write the program for a particular sensor. Like I happen to use the force sensor for this last demo I did, but I could have used, with the same exact code, I could have used a hand dynamometer or a light sensor or a temperature sensor. It would read whatever's channel 1 and control the ball based on that.
So Dave, I'll give you a shout out for the user manual that you put together.
Oh yeah.
Be
sure to mention that.
Resources that we provided for this webinar.
It's not on our website yet, but included with what Angie offered you with as part of signing up for this webinar, there's a document that's meant to be a complete guide to how to use web VPython with our GDX sensors. It's a complete guide, except it's only been around for about 3 days. So I don't pretend it's absolutely perfect, but I think it covers most of the stuff, and we'll improve it over time, and we'll get it posted on the website.
Okay, here is one question that you have to handle, Dave. Says Lego Spike Prime has some Python options. Are there capabilities to pair and use those with the NXTs?
You know, I don't know the answer for sure, but I would almost bet money the answer is no. We have worked with Lego for decades, and it's challenging. And they just announced their whole Mindstorm line is going away, and they used to support our sensors, but that's going away, and I'd be amazed if they support their own sensors with Spike Prime, the old sensors.
Yeah, so our ability to connect with Lego equipment is much reduced, excuse me, here in the recent years. So let's see if there are any other questions. Oh, we have Paul Austin's comments that he'd be glad to look into that. He knows the fellow that oversaw the Python on Spike Prime. So maybe we'll get a link in there yet. So.
Good.
Okay, anything else we need to share, Dave?
I think that's it. I don't see any other questions in the chat. Well, you know, we're always here. I'm D. Vernier at Vernier.com, and Tom's T. Smith at Vernier.com. And chat is a big deal these days, and email, and you can call us too.
Very good. Well, thanks everybody for showing up. We appreciate you taking time out of your day to learn a little bit about Python and Vernier sensors.
Bye.